Sorting algorithms. Sorting algorithms are the backbone of data organization in computer science. They help arrange data in a specific order, ascending or descending, making searching and processing more efficient. Today, we'll break down 6 essential sorting algorithms: bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. Let's get started. Understanding best, worst, and average case scenarios. Before we dive into each algorithm, let's quickly understand what best, worst, and average case scenarios mean in sorting algorithms. There are many algorithms that exist, but each one has their own strengths and weaknesses. Some are fast, some consumes memory too much. There are those that are good for large data sets and others only works at small data sets. Because of this, the use of algorithms depends on case-to-case basis. Best case. This is the most efficient scenario where the algorithm takes the least time. For example, in insertion sort, if the list is already sorted, it only takes O(n) time to go through it. Worst case. This is the least efficient scenario where the algorithm takes the longest time. For example, quicksort has a worst case of O(n)² when the pivot is always the smallest or largest element, causing unbalanced partitions. Average case. This represents the expected time complexity for a randomly ordered dataset. Most sorting algorithms have an average case close to O(n) log n or O(n)², depending on their design. Now that we understand this, let's explore each sorting algorithm in detail. Bubble sort. This method repeatedly compares adjacent elements and swaps them if they're out of order, just like bubbles rising in water. With a worst-case time complexity of O(n)², bubble sort is simple but inefficient for large datasets. It's mainly used for educational purposes. Application. Used in simple applications like sorting a small list of numbers on a whiteboard. Selection sort. Here we repeatedly find the smallest element and swap it with the first unsorted element. Think of organizing books by picking the smallest book each time and placing it in order. Time complexity? Always O(n)². Not the best choice for large datasets, but useful when memory swaps are costly. Application. Useful when sorting a small number of items, like arranging names in alphabetical order for an event guest list. Insertion sort. Now let's talk about insertion sort. This algorithm builds a sorted list, one element at a time. Imagine sorting playing cards in your hand. Each new card is placed in the correct position relative to the already sorted cards. It's simple but efficient for small datasets. Time complexity? Best case O(n) when nearly sorted, worst case O(n)². Use it when working with small datasets or nearly sorted lists. Application. Commonly used in everyday tasks like sorting people by height in a queue. Merge sort. Now let's talk about merge sort. It follows the divide and conquer approach, splitting an array into smaller halves, sorting them, and merging them back. Time complexity? O(n) log n, making it great for large datasets. Used in external sorting, like organizing huge files on disk. Application. Often used in sorting large amounts of data, like organizing a long list of movie titles alphabetically in an online streaming service. Quick sort. Quick sort is another divide and conquer algorithm. It selects a pivot, partitions elements around it, and recursively sorts the partitions. Best case O(n) log n, but worst case O(n)² when poorly optimized. It's widely used due to its in-place sorting and efficiency in databases. Application. Used in apps and websites when sorting items, such as arranging search results by relevance or price. Heap sort. Last but not least, heap sort. This method builds a heap, a special binary tree. The largest element, 8, is now at the root. Next, we swap the root, largest element, with the last element and remove it from the heap. Then we rebuild the heap to restore its properties. Repeat this process until all elements are sorted. We keep extracting the root, placing it in the sorted section, and rebuilding the heap until fully sorted. With O of n log n time complexity, it's great for priority queues in real-time systems. Application. Used in applications where priority matters, like managing a to-do list where the most urgent task is always handled first. Conclusion. Sorting algorithms are crucial in data structures and algorithms DSA. Choosing the right one depends on dataset size, memory constraints, and application needs. From simple to complex sorts, each has its role in computing. This table represents time complexity in Big O notation, which describes how an algorithm's running time increases with input size on n. Thanks for watching. Like, share, and subscribe for more quick DSA insights. Happy coding!